Hello everyone, my name is Shanqing Qu from Tongji University. Today I'm going to present our BMD, which aims to provide a general class-balanced multicentric prototype strategy for source-free domain adaptation. This presentation will contain three parts, namely the background, our proposed method, and the experiments. As we know, existing deep neural networks are constructed based on the IID assumption, that is, the train and the test data should come from the same distribution. If this assumption does not hold, the trained model will typically suffer from severe performance degeneration. To address this, unsupervised domain adaptation UDA is proposed. In this setting, we are typically given one labeled source domain sampled from PS and one unlabeled target domain sampled from PT. The goal is to obtain a good classifier to infer the label of the target domain. Though UDA has achieved significant progress, their practical applications are still limited. The main limitation is that existing UDA methods typically need the full access of source raw data, which is not always applicable due to the increasingly strict data regulations. Thus, recently, researchers have proposed the source-free domain adaptation (SFDA) to alleviate these limitations. The goal of SFDA is to learn a good target model FT with the knowledge from source pre-trained model FS. To achieve this, based on the source hypothesis proposed in short, existing methods have designed various self-training strategies. Among them, pseudo labeling strategy based on feature prototypes are popular. However, we found that most existing strategies are typically category biased. That is, they are easy to overfit to some categories. In addition, we found that a rough monocentric feature prototype could not effectively represent the target data. Based on these observations, we proposed a general class-balanced, multicentric dynamic prototype strategy (BMD) for existing SFDA methods. Specifically, to avoid the gradual dominance of easy transfer classes on prototype generation, we introduced a global interclass balanced sampling strategy. It is worth noting that our sampling strategy is not based on local instance level prediction results, but rather to select the top k most likely instance for each category from a global perspective. Therefore, we argue that our strategy is interclass balanced. Due to the domain shift, we found that a coarse monocentric feature prototype may not effectively represent those ambiguous data. Thus, we designed an intraclass multicentric prototype strategy to obtain more precise pseudo labels. Existing strategies update the pseudo label at a fixed training period, which may not effectively utilize the model adaptation information. Therefore, we further explored EMA-based dynamic pseudo labeling strategy. We evaluate our BMD strategy both on 2D and 3D cross-domain object recognition datasets. We have injected our BMD strategy to 4 existing SOTA methods. Here are the experiment results on VSDA. We can find that our BMD can significantly boost existing methods by a large margin. Not only on the 2D cross-domain object recognition, our BMD is also applicable for 3D point cloud. We have conducted extensive ablation study to verify the effectiveness of each subpart of BMD. Here are some visualization results to support the effectiveness. To further examine BMD indeed improves existing methods to achieve more class-balanced results. We also conducted the coefficient of variation metric experiments. In summary, in this paper, we propose our BMD strategy for existing SFDA methods. BMD can significantly boost existing methods to achieve new SOTA performance. Thanks for your listening. Our code is already available at GitHub.